Your API latency spikes from 50 milliseconds to over 500 milliseconds when fetching nested resources. This is the N+1 query problem manifesting. Consider a GraphQL query requesting 10 users, and for each user, their associated department. Without optimization, the system executes one query to fetch the 10 users, followed by 10 separate queries to fetch the departments, totaling 1 plus n queries. If n is large, the cumulative network round-trip time and database connection overhead become catastrophic. This pattern bypasses efficient database operations like joins, forcing sequential execution of redundant lookups. We must intercept these individual resource requests and consolidate them into a single optimized batch operation before hitting the data layer. This consolidation is the core function of the DataLoader pattern, specifically designed to mitigate this performance bottleneck in complex data graphs. Identifying the N+1 pattern requires monitoring the data access layer, not just the API response time. Look for repeated identical queries, differing only by the primary key value in the where clause. For instance, select asterisk from departments where ID equals 1, followed immediately by select asterisk from departments where ID equals 2, and so on. These sequential single record fetches are the telltale sign. In microservices architectures, this often translates to multiple synchronous HTTP calls to a downstream service, each call incurring serialization and network latency. The problem is exacerbated in deeply nested data structures, where a single root request triggers hundreds of subsequent dependent requests. The solution must operate transparently within the application logic, aggregating these requests before they leave the application boundary towards the persistence layer. The performance penalty of N+1 extends beyond simple query execution time. Each individual database query requires establishing or retrieving a connection from the pool, parsing the SQL statement, validating permissions, and generating an execution plan. Repeating these steps n times introduces significant CPU overhead on both the application server and the database server. Furthermore, the database often executes n separate index lookups instead of a single highly optimized index scan or hash join operation that could retrieve all necessary data efficiently. By batching 100 individual ID lookups into a single select asterisk from table where ID in 1 to 100 statement, we reduce connection overhead by 99% and allow the database engine to utilize its internal optimization capabilities fully. DataLoader is not a database caching layer. It is a generic utility for abstracting and optimizing data fetching by implementing two core principles, batching and caching. Batching ensures that multiple individual load calls made during a single tick of the event loop are collected. When a consumer calls loader.loadKey, the request is queued and a promise is immediately returned. The actual data fetching function, known as the batch function, is only invoked once the current execution context yields, typically at the end of the microtask queue processing. This deferred execution allows the system to accumulate all pending keys, passing the entire array of keys to the batch function for consolidated retrieval. The DataLoader instance is initialized with a single required parameter, the batch load function. This function accepts an array of keys and must return a promise that results to an array of values. Crucially, the returned array of values must be exactly the same length as the input array of keys, and the values must correspond positionally to the keys. If a specific key does not yield a result, the corresponding position in the result array must contain an error object or a null value, maintaining the positional integrity. This strict positional mapping is fundamental for DataLoader to correctly resolve the individual promises returned to the original callers of loader.loadKey. Failure to maintain this order results in data corruption for the requesting entities.
When loader.load is called, DataLoader registers the key and schedules the execution of the batch function using a mechanism like process.nextTick or setTimeout0 in Node.js or microtask queuing in browsers. This ensures the batch function runs asynchronously after all synchronous application logic has completed, allowing maximum key accumulation. For example, if three different resolvers call loader.load5, loader.load12, and loader.load5 within the same execution cycle, the batch function receives the array 5, 12, 5. The batch function then executes the single database query, retrieves the results, and DataLoader maps these results back to the three pending promises, resolving them individually. DataLoader implements a powerful in-memory cache for deduplication within the lifecycle of the DataLoader instance, typically tied to a single request. Before adding a key to the batch queue, DataLoader checks its internal cache map. If loader.loadKey is called multiple times with the identical key, only the first call triggers the actual data fetch and queue registration. Subsequent calls immediately return the promise associated with the initial fetch. This prevents redundant database hits for the same resource requested multiple times within the same API operation, even if those requests originate from different parts of the resolver tree. The cache key defaults to the input key, but custom cache key functions can be provided for complex object keys. To prevent data leakage and ensure cache freshness, DataLoader instances must be scoped to the lifetime of a single incoming request. If a single DataLoader instance were shared across multiple concurrent user requests, user A might retrieve cached data intended for user B, especially if authorization or tenancy filters apply. Therefore, the standard practice is to instantiate a new DataLoader map within the request context middleware, passing this map down to all resolvers or service layers. This guarantees that the cache is isolated and invalidated immediately upon request completion, ensuring that subsequent requests always start with a clean slate and fresh data access permissions. In a GraphQL environment, DataLoader is typically injected into the context object accessible by all resolvers. When a parent resolver fetches a list of entities and a child resolver needs to fetch related entities, the child resolver calls context.dataloaders.entityloader.loadParentID. This pattern ensures that even though the GraphQL execution engine calls the child resolver n times sequentially, all n load calls are batched into a single database query executed by the DataLoader instance. This transformation from sequential n queries to a single batched query is critical for maintaining low latency in complex GraphQL schemas involving many relationships. Handling composite keys requires defining a custom cache key function that serializes the key components consistently, ensuring that loader.load with ID 1 and type A and loader.load with type A and ID 1 resolve to the same cache entry. For error handling, if the batch function encounters an issue fetching data for a specific key, it must place an error object at the corresponding index in the result array, rather than throwing an exception for the entire batch. DataLoader then rejects only the specific promise associated with that key, allowing other successful fetches in the batch to resolve normally. If the batch function throws a global exception, all pending promises for that batch are rejected uniformly.